So today, as I mentioned, I'm going to go a bit further on the topic of beam column. So beam column is basically, let me refresh again, is basically a member where it is subjected to both load causing bending and also load causing compression, as shown in this diagram here, both Q and P, or both uniformly distributed W and P. So they combine. This action that we can see here is a combined actions of load causing bending and load causing compression, axial deformations. And the load causing bending class is the primary effect, which is the member is mainly designed to carry load causing bending. And on top of that, we have load which is going to cause compressions in the member. So today I'm going to go through with you how these expressions here are being obtained. Okay. But before that, let me stress that for beam columns, the effect of having the presence of axial force in the member, together with the primary actions of load causing bending, is that the deflections, in this case, delta here, the maximum deflections, and the corresponding moment maximum at this midspan here, for this case, will be amplified. Meaning that the values will be increased if you compare with the deflections where P is equal to 0. If you put P is equal to 0, P is equal to 0 in this equation, and also in this second set of equation class, you are going to get back delta is equal to delta subscript 0 and max equal to M max subscript 0. This delta subscript 0, M subscript 0 is the corresponding deflections and bending moment when there is no P, when P is equal to 0. So when P is not equal to 0, so this expression here, which we call the amplification factor, will be more than 1. So when it is more than 1, then multiply with delta 0 or M0, you get delta, which is the maximum deflections in this beam, and also this delta in this beam will be amplified. So that is the main thing that you need to remember, understand. What is the consequence of having axial force acting on the member together with a load causing bending? So now I would like to go to the notes, one of the set of notes that I have shared with you, which is this particular notes on chapter 3, which I also mentioned to you. This is the chapter that we refer to, beam columns. And in the beginning, we go through what is beam column, what is beam column, and where we can find this member of beam columns. Now, in section 3.2 and 3.3 class, I'm going to, it is shown here the derivation process. Where does this amplification factor comes from? So the first one is we start with beam column with concentrated lateral load. And the aim is here, okay? The aim is to show where does this come from and where does this come from. Once we get this first amplification factor for deflections, then we can get the amplification factor for bending moment. The same thing we get for this case. Once we get the amplification factor of this, and we can get amplification factor for bending moment. So these are the two cases of loading causing bending. A load acting at the middle, at the midspan, which we call the load here Q, and the load which is uniformly distributed along the member, which we use the symbol W. So these are the two load cases. And later on, we will see other load cases causing bending. So what is the corresponding amplification factor and the common characteristics of them? The common characteristics that we can see for all the amplification factor for different load cases. Remember, class, different load cases causing bending. This is point load, distributed load. Then we have other types of loading. The amplification factor will be different. Amplification factor will be different, right? So this is the sections where we are going to derive. So section 3.2 is for this case, and then section 3.3 is for beam column with distributed lateral load, which is this case here. Okay. So I hope you can follow. Okay, if anything that you cannot hear me or cannot see clearly, please let me know, class. Now, there are some mathematical manipulation process that you can refer to the detail given in the notes. I'm going to go through with you the main process. Okay. Now, for this case of beam column subjected to a lateral load, a point load acting in the middle, as shown in this diagram here. This is the free body diagram. If we cut through any of the sections, then if you cut through any of the sections, then you are going to get the bending moment acting here. So this bending moment, okay, is equal to negative EI y double prime for this coordinate system, x in this direction, y in this direction. So in a way that we have go through many times, if you take moment at this point, if you consider moment at this point using this free body diagram class, you are going to get to this equation. So the explanations are given here. That class you can refer to the explanations, but mainly it is from this free body diagram which comes from here. Then we take moment at this point, you are going to get these equations. You will get to these equations and then we make it into standard form. We make it into standard form in this way by dividing with EI, everything left hand side, right hand side. You get to this standard form of second order linear ordinary differential equation with constant coefficients and with right hand side not equal to 0. And you will get two solutions for this. Okay, one is the homogeneous solutions and the other one is the particular solutions. The particular solution in this case is as shown in this equation 3.3 here. So A and B, by now you know, you need to make use of boundary conditions. So here, boundary conditions, we take advantage of the fact that this is symmetry. The deflection shape will be symmetry, meaning that the slope at the center here will be 0. So that is the boundary condition that we are going to use together with what happened to y at the support here, which is y is equal to 0. So this is the process next, which is shown here. So if you consider x0, y0, you get b0 from 3.3. Then you differentiate this, dy dx. Then you substitute So this is what I mentioned just now. We take note that this deflected shape is symmetry about the midspan. So this is, so at x is equal to L over 2, which is the midspan, so slope becomes 0. So from here, after we know that B is equal to 0, then from these conditions, differentiate first this, substitute these conditions, then we get A. Then we substitute A into 3.3, then we get 3.4. So this gives us the shape of this deflected shape. Now, in order to determine, to investigate the effect of having axial force together with forces, together with load causing bending, in order to investigate this beam column here that we consider, we look at the midspan deflections, which is the maximum deflections in this case. So we relate to what happened to the member by looking at what happened to the maximum deflections when the beam column is subjected to Q and P. Okay. So that is the next thing that is shown here. So you put x is equal to L over 2, then you get maximum deflection delta at midspan given by this equation. This is just simply substitute x is equal to L over 2 into 3.4, you get 3.5 here, then you simplify by introducing this term here, U. So remember these terms U because we need these terms again, U. So U is KL over 2. So tangent U means tangent KL over 2 minus KL over 2. This is simply rewrite this and then simplify this by introducing this symbol U. Now, at this particular stage, we know what is the maximum deflections if there is a P acting together with Q. This is the equations. But in order to know what happened when we compare with the case without P and with P, so we further manipulate these equations by doing this operation here. Then we come to this equation 3.7. So equation 3.7 class is essentially the same as 3.5. The only thing that we make these terms appear, QL cubed over 48 EI. This is actually the deflections of this beam column without P. So we multiply these deflections, which is the deflections of the beam column at midspan without P, which is basically a beam only. Then multiply with these expressions here. So by doing this, then we can relate to what happened if P is not acting compared to when P is acting to delta. So this is just the process here. 3.7 is actually the same as this 3.5. Just that we want to make this term appear. So next, what do we do next? So we substitute, we use this symbol delta 0 represent this, which is the deflections without P, only Q acting only. So by using this to substitute this to represent this, so we get delta equal to this. So now you can see delta, the effect of having axial loads, the behavior of this beam column by looking at what happened to maximum deflections is equal to, is represented by these equations. Now we have 3 tangent U minus U over U cube. This is cube. Tangent U minus U cube. Okay. Now, here we want to, the next series of process is to get to these equations here, 3.13. Why you want to get to this equation is, in this equation class, you can see the terms here, P over P critical. So if we can make this appear here in the equations, then we can get a better pictures of what happened when P increase. Compared to, if you compare these equations with these equations, they are both actually the same thing, just that we do some manipulation and some approximations. We get from here to here. So if we compare 3.13 with 3.9 here, what we can see, what we cannot see immediately from here, we can see immediately here is when P is increasing, what is the effect? So when P is increasing, so this whole terms here will become more than 1. And P is increasing, we need to know that increasing relative to the P critical. So P critical class is the critical load of the beam member of the beam column, okay, without the lateral load acting. So it's like a column. If we consider the beam column as a column only, what will be the critical load? So by changing to this form through these manipulations and approximation here, so we can see clearer that the effect of P is to make the delta increase, okay? And it is related to the ratio. So when we talk about what is the effect of P, we must look at how large is the magnitude of P relative to the P critical of that member. So that is shown clearly in these equations. And these are the manipulation process. First, tangent U, we get rid of the tangent U by using this power series of tangent U. So there are some approximation here. So this is a infinite series. Okay, continue again. Then we substitute first into these terms into this, and then do the simplification. We come to this. And next, we want to make the P over P critical appear. So we manipulate again these U squared terms here, remembering what is U. Okay, that's why I asked you to remember U. U is KL over 2. So you can manipulate this to make this thing appear here. So once you make this thing appear, then we substitute into 3.10 here. And this is the outcome. And this is 0.984, 0.998 plus, you can go further. These are all very coefficients, very close to 1 plus P over P critical to the power of 3 plus again further. So again, this is infinite series because this come from here, infinite series. But we show the terms only 2 terms, and but there are many, many terms here. Then this one here is approximated. Make this equal to 1, so very nearly equal to this. And when we look at these terms in the bracket, this is actually the geometric series expansions, the geometric series of these terms here. So that's why we come to this equation 3.13. So what equation 3.13 tells us is that, okay, the maximum deflections of the member is equal to delta 0. And the maximum deflection that would exist if only Q were acting, it will be multiplied by an amplification factor that depends on the ratio. So this is one of the main points that you need to keep in mind. So the important things that is affecting the behavior of beam column when there is actual load P is how large is the ratio. Later, we will see if the ratio is smaller than certain value, then the effect is not that significant. So it is important to look at the ratio of P over P critical. So from this equation, class, the effect of axial load is to magnify the deflections that would exist in the beam if the axial force were not present, which is delta zero. So P will magnify delta zero. Magnify means the actual delta, the maximum delta in the beam column will be larger than the deflection of a beam. Now, another important point that I would like to draw your attention to is that, class, if you look at equation 3.13 again, then if P is almost equal to P critical, or in the extreme case, P exactly equal to P critical, this is a theoretical case, it cannot happen, then what we get is that the denominator here, okay, of these expressions here, the bottom part here will be 1 minus 1. If P is equal to P critical, meaning that 1 minus 1, then you get 1 divided by 0, infinity. It means the deflections will become very, very large, infinity, very, 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 very large when P is equal to P critical acting, which is not possible, but that gives us a criteria. And that gives us a criteria that can be used to determine critical load. Okay. So that is the point here. So if we look at this point here, class, we look at this the point here, we will see that right here, particular here, okay, from this part here. Equation 3.13 also shows that the deflection of the beam column increases without bound. Without bound means it becomes infinity. Without bound means it's until infinity. As P over P critical approaches unity, approaches 1. In other words, the resistance of the member to lateral deformations caused by Q vanishes, becomes 0. The resistance becomes 0. Vanishes means becomes 0 as the axial load approaches the critical load. So this gives us a kind of another criteria that we can make use of. Okay. So it says here, it is thus possible to determine the critical load of a member by finding the axial load where its bending stiffness becomes 0. So this is one of the criteria that we are going to make use of later in Rayleigh's method. So this is one of the criteria later when we look at the use of Rayleigh's method to determine critical load. We make use of this criteria. We make use of this criteria. That is, the critical load of a member is the load that is going to make the bending stiffness of that member become 0. So this is one of the important outcome we can get from by looking at equation 3.13, okay, which is okay. So let me go back again. Class, until now,